Last week, we talked about buffer overflow. We had seen how buffer overflow can compromise the memory integrity. We also mentioned, but did not get into detail, that buffer overflow can also compromise execution integrity. Today, we are going to talk about that. To understand that, we first have to know what is a core stack and runtime environment. Modern computers are based on the von Neumann computer architectures. Under these architectures, the programs and data are stored together in the memory. There are no clear distinction between program and data. That means the data could be programs and the programs can be data. So this have some implication in security because the execution may be treated into treating the input data as code. And we have seen there are some other systems like interpreted language like JavaScript or SQL have similar feature where it's difficult to distinguish code from data. And this difficulty form the basis of what we call the code injection attacks, where the malicious code are presented as data. So in the memory, let's say that we have the memory and we have the instruction, okay, in the memory. The processor have a counter called program counter that keep track of what will be the next instruction to be executed. So suppose a pointer point to here, in the next cycle, instruction 1 will be fetched to the processor CPU and execute. And after this is done, the program counter will be increment by 1. So in the next round, the next instruction will be fetched and executed, and the third, and so on. So in this way, the program will be executed sequentially, starting from the top. This is very boring, okay? So what we have is that we can have branch or jump. So there are two types of branch. One is called direct branch, or the other one is called indirect branch. Where in a direct branch, in both of them, the instruction can modify the program counter. Let's look at these examples. In these examples, the execution is run sequentially, starting from this instruction, next instruction, and next instruction. And this instruction is branched to 1008. So this instruction actually will modify the program counter to 1008. And hence, the next instruction to be executed will be this one, 1008. So there's a direct jump to here. And this instruction happened to be branched to 6123 with a $sign here. It means that it doesn't mean jump to the location 6123. It means that go to 6123, which is this location, look at the value, and jump to this location. So in this case, it's 1001. So this is called indirect branch. Also, you have learned a lot of functions, and function break the code to a smaller piece, so facilitate modular design and code reuse. A function can be called in different program locations, and they can be called recursively. So, for example, in this simple programs, in the main program, you call the sample functions. So the control flow will go from here, jump to here. And then there's a printf, then you jump to printf, which are functions. After it's completed, return, you jump back to here, continue execute, and then this one return, then you go back to here, and then and so on, and printf and so on. So you may wonder, okay, when just now when I trace the program, I use a pit. You can imagine I use a pen to trace the control flow of the programs. Okay, so you may wonder during the runtime how the computer or know where it should continue after it finish. Like when this return, where should it go, and where the function store the local variables. And this is a case even uh, more interesting case when it's a recursive functions. Okay, suppose that we are running the recursive function using a tower Hanoi. We know that your experience is that we need to get a lot of many paper to keep tracks of what are the local variables. This is done by what we call a call stack. Okay, let's go to this example. Maybe it's easier to go straight to these examples. Okay, so in this example, I have a functions. Okay, the main program call a function 1, putting in local parameter 3. So we call function 1, and function 1 call function 2, and function 2 call function 3. And when function 3 is completed, you return to function 2, return to function 1, and return back to here. And all of them have local variable b equal to 1, kb 1. And these 3 local variables are different. You can imagine that this is a situation that as a lecturer, I'm delivering a lectures. And I go through the slide by slide sequentially. So you can imagine that I'm now in function 1. Okay, I go through slide by slide. I'm going through the lecture starting from slide 1, slide 2, slide 3. And halfway, somewhere in the middle, Alice, who's sitting on the left, raised her hand and asked questions. So she interrupt me. So then she requests to look at slide, for example, 50. So then I have to jump to 50, answer her questions, and while halfway, Bob on the right side also raised his hand and asked a question and request to go to slide 25. Okay, so Bob also asked me a questions, and then I entertain Bob. After Bob, after I finish answer Bob, I have to get back to Alice. So I have to remember which slide that I end before I jump to Bob's. Okay, so I go to Alice, and then after I've answered Alice's question, I have to go back to the main lectures. So how do I keep track of the slide number? Okay, one way is to using a stack or what you call core stack. So while I'm delivering the lectures, Alice asks a questions. So now what I have to do is that I create a runtime environment. Including the return state. That means where I've left at this point, and push this to the stack. So okay, Alice asks questions, so I push this into the stack. Okay. So this is a current environment. So this is when Alice asks me a question, I take out all the information, put it and push into the stack. So while I'm addressing Alice's question, Bob asked me a questions. So now I take the environments, okay, package it and push it into the stack. So now stack have 1, 2, 3. So after I finish with the Bob questions, I need to know where to jump back to. So I look up the information here. I pop this out, look out the information. This information will tell me where to return to. Then after this pop, then get back to this Alice environments, and then I started to continue addressing Alice questions. After this is done, okay, so I pop this up, look at the address that I have to go back to, and then I continue to with my main lectures. Okay. So this is you can see that this is one illustrations. Okay, yeah. So now, okay, so these are main programs. Whenever a function is called, the runtime environment will create, okay, will package whatever information. This information include the parameters, the local variables, and very important is the return address. Okay, the return address, and all this will be packaged it and push it into the stack. Okay. For more detail, let's look at this. Okay, suppose we want to this running sequentially. This is a main program running sequentially. At this point in time, is going to make a function call to test file. So now then what we have to do is to push all the information into the stacks. Okay, so we'll push 5. 5 is the parameters. Okay, so 5 is pushed in the stack, and the return address. This is very important. The return address also pushed into the stack, and 1 is a local variable of 1. Okay, this 1. Okay, and then after everything is pushed into a stack, then you branch to the function call. So you branch to the function call over here. So sorry, this one should be draw a line. Okay, so we go to the function call. At the end of the function call, we pop up the stack, and then look out and branch to the return address, which is the stack pointer plus some offset. Okay, so this is stack pointer, and some offset is the return address. So from here, then we jump back to 1008. Okay. So we have seen that how the call stack store the location of the next to be executed instruction, and also see how the program counter keep track of the next instruction to be executed. Okay. Now, suppose that, imagine that we have an attacker. The attacker has the capability to read and write to some memory. That means he's able to compromise the memory integrity. And how does he do that? Possibly through buffer overflow. So through buffer overflow or other means, the attacker is able to modify some memory locations. So in the next few slides, we'll show that how this compromise of memory integrity can lead to compromise of control flow or execution integrity. Okay. And also, one point to note is that although we assume the attacker have the capability to write to some memory, in general, it is very difficult for them to do so. They have many constraints. For example, the attacker can write to only some particular locations, or he can only write a sequence of consecutive, but he cannot go to any arbitrary location. Whatever he's going to overwrite, this is like buffer overflow. It has to be a sequence of writing of bytes. So because of this constraint, the attack has to be very surgical. That means that by just modifying a small number of memory locations, and yet the attacker can achieve a lot of damage. So how can, what are the possible way to do that? Okay, there are 3 ways. Okay, one is overwrite the program. Second one is overwrite the control flow informations. Okay, let's show it. Okay, the first one is, this is the most simpler one to understand. Okay, is replace the code. Okay, remember that the program are code, program are data are also programs. Okay, so these are the codes, and normally you execute in this way, this way, and this way, this way, and then they do a branch to some part of the library. Okay, so assume the attacker has a capability to modify the data from 1008 onwards. So the attacker can inject his code, put it here. So this is more like a code injections. So now during the execution, the control flow will go from here to here to here to here to here. Then he jump to the part where the code is injected by the attacker. This is very easy to understand, but in general, it's very difficult for attacker to execute this. Okay, because he had to write quite a big amount of data. Another method, attack 2 and attack 2A and 2B, okay, modify the control flow. Let's look at this example. Under the normal circumstances, the control flow will go this way, execution will go this way, you go from here sequentially, and then there's a branch to 1008, which go to here, and next is an indirect branch to 100 and 1. Okay, look out this address and then go to here. First case, okay, the attacker is able to attacker modified this part. Okay, so this is the under normal circumstances, and somehow attacker is able to modify these memory locations, this memory location 1004, and change this 2000, this originally is 1008, and change it to 2000. So now the control flow will go to this way, this way, this way, this way, and then jump to some part, for example, some library call, and attacker unable to modify this, but by the fact that you can jump to making some existing library call could lead to a lot of damage. For example, this could be, for example, formatting the disk. The next one is that instead of modifying the code, this part is still the code, this part is the data. This part is the data. Okay. So instead of modifying the code, the attacker modified a data. Okay. Changing this 1001 to 2000. So now the execution, the control flow will go from here go to here, and then jump to this. Okay. The difference between these two, okay, although achieving the same effect, the difference between 2A and 2B is this. In 2A, attacker had to modify some memory location were designated as program. While 2B, attacker a modified location designated as data. In particular, this data, this part could be the stack. Okay. So if this stack, what will be the consequences? If the adversary is able to, through, for example, buffer overflow, modify this location where this part is used as a stack, okay, and this is the return address. Okay, remember that when we keep the call stack, there's a one information which is particularly important, which is a return address. Okay, so if the attacker able to modify this return address during the execution, when the function ends, you go to the intended location, okay, by the attacker rather than the original intended locations. Okay. So, okay, so we have demonstrated. Okay, now we have demonstrated. We have talked about program counter. we're talking about the core stacks, and then we demonstrated that how small modifications of locations of memory can lead to control flow integrity, compromise of control flow integrity or execution integrity.